All right, nuclear decay is what happens primarily when you have unstable isotopes. Nuclear decay is what happens when you have unstable isotopes. They're unstable because they go through nuclear decay. All right? And while there are other forms of decay, if you watch the Cosmos series, you'll learn about neutrinos. We're not going to talk about neutrinos. We're going to talk about alpha particles and beta particles and gamma rays. Okay? So alpha has this symbol that looks something like this. All right? An alpha particle has the same structure as the nucleus of a helium atom. An alpha particle has the same structure as the nucleus of a helium atom. So there are 2 protons and 2 neutrons, but there are no electrons. So it's going to have a 2 positive charge from the 2 protons. Okay? Now, since it's got 2 protons and 2 neutrons, and protons and neutrons pretty much weigh the same, the atomic mass is 4, and we put the mass number here, and the atomic number goes on the bottom. This is our nuclear notation. Okay? So that's how we write alpha particles. Now, if you just wrote the symbol, it would mean alpha. It's the Greek letter alpha. But in order to use this in nuclear equations, it's a lot easier probably in the long run, especially when you're just kind of beginning to learn this stuff, to go ahead and put that 4 and that 2 there. And you don't have to, you know it's there, kind of helps with the math. Okay? Beta has the same structure as an electron. Beta has the same structure as an electron. The symbol for beta is this. It has so little mass that we ignore the mass. So the mass number is going to be 0. But what's tricky about it is, or maybe tricky, maybe not, is that this beta particle, which has a negative charge, is coming out of a neutron in the nucleus. And when you take a negatively charged particle, like a beta particle is negative and an electron is negative, take it out of a neutron, what it leaves behind is a positive particle, and a positive particle with that same mass is a proton. To make the math work out, we usually write the the proton number as a -1, because it changes a neutron into a proton. Mathematically, it'll end up making a proton. Okay? Now it has no neutrons, no protons, but it is basically 1 electron. Okay? And it has a 1 negative charge. Two protons and 2 neutrons. Protons and neutrons have an atomic mass of 1, so 2 and 2 is 4. That's the mass number. Yep.
So is that why beta has a 0, because the electrons are lighter than
yeah. Electrons have 1,850 roughly. You divide by that the mass of the proton to get the mass of an electron. It's so little, it's just like we don't worry about it too much. Yes? Huh? Experimentation. Yeah, they have a special balance you put electrons on. No. No. I don't know specifically how you find the mass of an electron. Okay. Yeah, you could Google it. Yeah, it escapes me at the moment. 10 minutes from now, I'm not popping in my head how it's done. But all right. Then we've got gamma radiation. Now, you could say gamma radiation doesn't have any particles, but technically all light X-rays are light, gamma rays are light, radio waves are light, all come in little packets we call photons. So you could say they are particles, okay? But we generally think of it not as a particle, but as a wave. Okay, now gamma is symbolized like this. It's like a script L that you spin 180 degrees upside down. That makes sense? And then it has no mass, even less mass than a beta particle does. And it doesn't do anything to protons, so that's a 0 here too. Alright, so we have 0 protons, 0 neutrons, 0 electrons, and no charge. Okay, you need to put your name on the top line and put that in your personal file. Now, neutrons aren't technically part of nuclear decay. In a sense they are, but we're not going to treat it like that. Because we use them in nuclear equations, you need to know that neutrons are just symbolized with a letter N, a small letter N, not a capital letter N now, but a small letter N. And it has a mass of 1, because protons and neutrons have a mass of 1 AMU, but it doesn't do anything to protons, so we put a 0 down here. Okay? No protons, 1 neutron, no electrons, 0 charge. So those are the nuclear particles, although these are the ones that we primarily use when we talk about nuclear decay. Right? We don't typically talk about neutrons in the form of nuclear decay, but we could. All right? So yes, we do use these when we're talking about when writing nuclear equations. So let's do one of those. Let's take uranium. Uranium goes through alpha decay. Uranium has a mass of 92, and the most common forms or isotopes of uranium are 235 and 238. 238 is far more common than 235. When they talk about enriching uranium, what they try to do is to get a higher percentage of 235 in the sample. The higher percentage means it's more unstable. You've got an overall greater amount of instability, which then makes it more useful for using in the nuclear power plant or nuclear weapons. So let's do alpha decay for uranium-238. So let's see. We're going to create then, in the process of this decay, we're going to have an alpha particle over here. Okay? Well, if an alpha particle leaves, then the mass is going to be reduced by 4. Okay? So that's 234. And the atomic number, if an alpha particle leaves, it's pulling out 2 protons, so whatever else is over here is going to have 2 less protons than that. So that's a 90. And if you look on the periodic table, the element that has 2 less protons than uranium is thorium. So this particle then is thorium. And that's basically how you do nuclear equations. Okay, you got to find what's missing in the equation. All the mass on the left across the top, all the mass is the same as all the mass over here. Okay, all the proton numbers are the same on both sides. So when you're balancing a nuclear equation, you're just trying to get all the mass numbers and all the proton numbers or atomic numbers to add up to be equal on both sides. Does that make sense? Yes? How do you know it's hazardous?
Yeah, that's alpha.
Oh, I mean, it's just very commonly known. That's what uranium does. Uranium goes through alpha decay, then thorium goes through alpha decay, and let's see, then you get radium, and radium goes through beta decay, and then the products go through alpha decay 2 more times. Actually, there is a chart in your homework references that shows that whole step-by-step process. So uranium goes through alpha decay to thorium. I'm sorry, I said that wrong. Thorium goes through beta decay, and then protactinium goes through beta decay. And then you get all these alpha decay series. And then beta decay and alpha decay, 2 beta decays, alpha decay, 2 beta decays, alpha decay, until finally you get to, this is lead right here, when you get to there. So your mass number is 206, the atomic number is 82, 82 is lead. No, that's why I give you this. Okay. If I ask you about it on the test, and like ask you to balance an equation or something, I will have to tell you the pieces you need. You figure out so you figure out the rest. No, you don't have to memorize the decay series for uranium. Okay. Might have to do it in physics, but we don't have to do it in here.